Yeah, good morning. In this session, I would like to introduce one algorithm to find out the minimum number of tears required to solve a given problem, a given flow sheet, or maybe a partition. So these are the session outcomes. You are required to apply the algorithm and find out the minimum number of tears required to solve the problem. And after finding out the tears, you need to also find out what is the computational sequence. In the previous session, of course, we have seen these definitions, so I can skip this part. So in the previous session, we have seen the example flow sheet. We were able to partition into two. The first partition involving units A, B, D, and the second partition, which you will be seeing in the next slide. Now, this is the partition that we need to solve. Now, how do we go about this? For example, if I want to start with solving unit A, then as per the sequential modular approach, all the feed streams, input streams should be defined along with equipment parameters and operating conditions. So, given this information, we are required to calculate the output streams, which are 2 and 10. Now, if you try to draw an envelope across all these blocks, now you can see there is only one input stream, which is designated as feed here, and there are two output streams, 2 and 10. So if you want to solve this problem, we need to define feed stream, equipment parameters, and operating conditions for these three units, A, B, and D. So given this information, you should be in a position to solve 2 and 10. So apart from feed 2 and 10, all the other streams involved in this problem, which are 1, 8, 9, are considered to be intermediate streams. They may be output streams of a particular unit, but they also are going to be inputs to another unit. For example, if you take 1, it is an output stream for unit A, but it happened to be the input stream for unit B. So we call such streams as intermediate streams. Now, if you want to solve the problem, given the necessary information required for defining the problem, then where do I would like to start? Let us assume that I would like to start with unit A. When you look at unit A, I know feed, but do I know 8, the other input stream to unit A? Now this is not known. So the only option for us, if you want to start with A, is tear this stream. You saw what is meant by tearing? Guessing values for that stream. Remember, guessing values for a stream means you need to guess at least C+2 variables so that you will be in a position to calculate whatever property that you require with respect to that stream. So if the number of components are C, then you need to guess at least C+2 variables. Having guessed these values, now I know both the inputs to stream A, so I should, unit A, I should be able to solve and calculate stream 1. Once I know stream 1, I will be able to solve unit B to calculate 2. And once I solve unit B, I will be knowing 9. So I know the input stream to D, I should be able to solve D to calculate 10 and 8. Remember, we started with an initial approximation for 8. Now we got an update. Check whether you are able to reach convergence. If convergence is achieved, you can stop. Otherwise, you need to start with another guess for these recycle stream or the tear stream and go with one more iteration till you converge, till your results come to a convergence. Right? Remember, even if one of the variables out of this C+2 is not within the tolerable limit, right, then you need to proceed with one more iteration. So this is how the moment you tear stream 8, you can see that I will be able to find out the computational sequence as A followed by B followed by D, and then check for convergence. If convergence is not achieved, repeat this process. But is this the only alternative that I have? Can I tear stream 1? Suppose if you decide for some reason you would like to tear stream 1, will I be able to start with unit A? No, because 8 is not known. If you have decided to tear stream 1, then but I will be able to solve unit B because I know the input to unit B, calculate 2 and 9. Then I will be able to solve unit D to calculate 8 and 10. Then once 8 is known, because feed is defined, I will be able to solve unit A to calculate 1. We started with an initial approximation, we got an update. Again, check for convergence. If convergence is not achieved, repeat the process. So if you happen to tear stream 1, then the computational sequence will be BDA. In the same way, if you happen to tear stream 9, then the computational sequence will be DAB. Right? So the tear stream is going to influence the computational sequence. Now, out of the given 3 options of tearing stream 1, stream 9, stream 8, which is better and why? So there may be a number of alternatives, so which we will be looking at in the due course of time. Now let me consider the second partition in the example flow sheet. Now we have several units and there may be some interconnections, recycles. Then what is the tear stream set? In the previous problem, ABD, we need to tear only one stream. But if you need to tear more than one stream to solve a given problem, we call it as a tear set. Set of all the tear streams. Now can you come up with the minimum number of tears required to solve this particular partition or this particular flow sheet? It may not be that easy like what we did in the previous case. Again, even in the previous case, we had 3 different alternatives. Here, there may be many more alternatives. Now, typically, when you want to tear, you can use, there are several algorithms, though I may not be talking about all of them. So, you need to find out the tear set that is going to give you the solution within fewer number of iterations. In other words, the tear sets are going to dictate the rate of convergence. So try to find out the tear set which is going to give you the best rate of convergence. There are a few algorithms under this criteria. And this is the one that I am talking about, at least one algorithm I will be presenting. And what I mean by minimum difficulty, suppose we had the choice of selecting 1, 8 or 9 in the case of the first partition. All the possibilities require you to choose only one tear stream. But which one is better or which one is more difficult? 1, 8 or 9. So if you have such a possibility, especially when the number of tear streams are similar, then you can probably use this as the secondary criteria to choose among the alternatives. Now, for example, what is meant by tearing? You need to guess values, at least minimum number of values as C plus 2. So out of the 3 streams, let us suppose if one of the streams has fewer number of components compared to the other 2, then you need to choose only minimum, lower number of variables which may help you to reach the convergence quicker. So this kind of a criteria can be used to eliminate the possibilities when all the other things are similar. So as I said, this is the algorithm that I will be talking about, Berkeley and Motard algorithm. So this is the one I will be presenting. So if you have alternatives, you can choose the tear set that gives you the minimum difficulty based on the number of components involved in alternative tear sets. And as I said, you can also find out the tear set that gives you the best rate of convergence. One such algorithm is Upadhyay and Green's. If you are interested, you can look into literature and also apply that. Now, this is what I was talking about, Berkeley and Motard algorithm. I will come back to this probably after taking a simple example, and then we can discuss this. Now I have this flow sheet. As I said, in any sequential modular approach, given the inputs, equipment parameters and operating conditions, we need to calculate the outputs. So do you think input or output, can it be a tear stream? No. As per the definition or as per the characteristics available in your sequential modular approach. So even if they are present, try to ignore them. You don't have to worry about either input stream or output stream. In other words, this algorithm need to be applied for all the intermediate streams only, because the tear streams will have to be only intermediate streams. They cannot be inputs. Inputs are going to be defined. Outputs are going to be calculated. So they need not be considered. Now what you will be doing is, so there are 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8. So these are considered to be nodes, or you call it by any other name, doesn't matter. Now you need to write the precursor. What I mean by a precursor is, in order to calculate a particular stream, what is the corresponding input streams for that particular stream? In other words, suppose if you consider 1, that is the output stream from unit C. Now in order to solve unit C, then only you will be able to calculate 1. But when will you be able to solve unit C? Only when you know 4. So the precursor for stream 1 happened to be 4. Without knowing stream 4, we will not be in a position to calculate 1. Similarly, you take this possibility. What are the precursors for stream 2? This happened to be the output from unit A. All the input streams to this unit will become its precursors. So 1 and 3 will be the precursors. So looking at the flow sheet, it is not very difficult for you to propose these precursors. Then formally we will go into the algorithm later. Then you are supposed to eliminate all the nodes that have single precursors. In this example, stream 1 has got a single precursor, followed by stream 5 and then 6, then 8. So this is the first level of precursors that we are doing. Now when you propose the second level of precursors, you are supposed to drop all the streams that have single precursors. That means 1, 5, 6 and 8 need to be dropped. But when you are writing the second level of precursors, when you drop any node just because it has got a single precursor, you should not be writing them, continuing them in the next level. What I will be doing here is, I have dropped stream 1, stream 5, stream 6, stream 8 from consideration, further consideration. But 3 is already continuing in the next level, 4 is continuing, 7 is continuing, 2 is continuing. So the precursors should also be listing only the streams that are continuing at this point. For example, if you try to see here 1, because 1 is dropped, I will not be able to write 1 here. So what I will be doing is, what I am required to do is replace this 1 because it is dropped with the precursor for that stream. So the precursor for stream 1 is 4. You remember 4 is continuing, so I will be able to replace 1 with 4. Similarly, if you look at 6, 6 is being dropped, so I cannot continue writing 6. So you should be able to replace 6 with its precursor, which is 7. So you must be able to take care at any given stage, this precursor list should not be containing nodes which are eliminated or nodes which are tared. Of course, we have not tared any stream yet. Right. Now look at all the precursors for different streams that we have at this point. Then you can see in this example that all the 4 streams have got 2 precursors. If there is one stream which is having the largest number of precursors, you can select that. But here all the 4 happen to have only 2 precursors. In such a case, look at what are the stream numbers that are appearing more number of times. For example, from this list you can see stream 7 is appearing 3 times. So choose stream 7 to tear. So this is what I am going to tear. What do you mean by tearing 7? You are guessing values. That means you already have values in your problem. So when you write the precursors in the next level, the tear streams or eliminated nodes should not be continued. Right? So what I mean by that, when I write here, I will be writing, let us say 3, 4 after taking this decision. Now 2, 7 is already known, so I don't require information again from 7, 2. And because I have already decided to tear, I need not continue this. Now remember, at this point of time, 3 is having a single precursor, 4 is having a single precursor, so I need to replace 3 with 2 and 4 also with 2. What do you mean by this? So you require information from that stream twice. That means it is in fact we need to know 2. So we are left with only stream 2. So you need to cut this, you need to take this as the second cut. The moment you decide to cut the stream, now everything is addressed. No more information is required. So the streams that are going to be teared in this particular problem are 2 and 7. So do you think you will be able to solve the problem with tearing these 2 and 7? Now once you know 7, because this is the only input to stream E, I should be able to solve unit E. That will give me the values of stream 8, 6 and output. Then once I know stream 6, I know stream 2 because it is already guessed. So I should be able to solve unit B to calculate 3 and 4. Once I know 4, I will be able to solve unit C to calculate 5 and 1. Right? Once I know 1 and 3, I'll be able to solve unit A to calculate 2, right? Similarly, once I know 4, I'll be able to solve unit C to calculate 5, and knowing 5 and 8, I'll be able to solve D to calculate 7. Now, in this process, all the units are being solved, and we were able to solve all these intermediate streams. In the process, after initially starting with some guesses for 2 and 7, we got an updated values for these streams. So check for convergence. If convergence is not achieved, proceed with one more iteration. Now similarly, let me take, this is the problem we are discussing. So there are 2 pairs, 2 and 7, and the computational sequence you have already identified. Now take another example in the same way. So these are the first level of precursors. Now I need to eliminate stream 1, stream 4, stream 5, 8, because they have single precursors. So when I am proposing the next level of precursors, I should not be involving S1, S4 or S8. Wherever you have them, you need to replace them with its corresponding precursors. So S8 is being replaced by S5. I don't have a problem with S5 because it is continuing even in the second level. Similarly, S1 is replaced with S13 because S13 is also continuing. So try to take care that whenever you are writing the precursor list, you are not supposed to make use of any nodes which are eliminated at that point of time. Now, once again, you can see in this problem that all the precursors are 2. The number of precursors required for all the streams are 2. Now, looking at this, you can see S7 is repeated 3 times, S3 is repeated 3 times. So either you can select S3 or S7, that can be cut. Now when you cut S7, for example, now this need not be continued further. We already have made a decision to guess values for the stream. So once I know values for the stream, that means we already know. So the precursor for S5 becomes S3, precursor for S6 becomes S3, precursor for S13 also becomes S3. Now S4, because it is eliminated, I am replacing yes, as it is, S5. Now when you look at this, S13, the precursor is S3, because now after this, because these are the single precursors, I need to eliminate even these nodes. So S13 cannot be written, I will be replacing it with S3. S5, the precursor is S3, so S3. So you need to cut S3. These are the 2 cuts, S3 and S7, this and this are the precursors. So you can check up whether you will be able to solve the problem with these 2 tears. So we have decided to tear S3 and S7. These are the 2 inputs for unit C. I will be able to solve unit C to calculate S13 and S5, S6. Once I know S5, this is the only input to unit D. I will be able to solve unit D to calculate S8 and S6. Then I will be able to solve unit E to calculate S7. We started with an initial approximation, we got an update. Now what is left after solving C, because you know S13, you should be able to solve A to calculate S1. S1 is known, S4 is known, you should be able to solve B to calculate S3. We got an update. So check for whenever there is an update with respect to the initial guess, check for convergence. If convergence is not achieved, again perform one more iteration. This is how you will be able to find out the tears. Let me now go back formally and try to show you the algorithm. Create a node of, for every intermediate stream, you create a list of precursors depending on the flow sheet connectivity. This need to be done only for all the intermediate streams. Okay. Then eliminate nodes from this precursors list which have single precursors. Replace eliminated nodes in wherever they are appearing in the next level of precursors with their corresponding precursors. There are a few other possibilities. We will probably try to look at them as we progress in another example. So try to make sure whenever you are moving to the next level of precursor, you should take care such that eliminated nodes or tear streams are not continued further. So let me take another example. So this is an actual flow sheet probably taken from Dryden. Can you find out what is the minimum number of tears required to solve the problem? Maybe analytically without applying the algorithm, if you are able to spend some time, you may be able to come up with the solution. But let us follow the algorithm. So this is the flow sheet. Try to write for every intermediate stream. You don't have to worry about this or these output streams because they cannot be tiered streams. I think that's all. So for all the other intermediate streams, you can write the precursors. As you can see, except for stream 7, in order to calculate 7, we need inputs from 6 and 17. So they are the precursors. Similarly for 12, for this stream, we need information from 10 and 11, the corresponding inputs to this mixer. So apart from these two streams, all the other streams are having single precursors. So we need to eliminate all the streams excepting 7 and 12. When you eliminate all the streams excepting 7 and 12, now 6 is eliminated. So I should be writing replace 6 with 4. But unfortunately even 4 is eliminated. I cannot replace 6 with 4 because 4 is also not continued. So what is the precursor for 4? 2. I cannot replace 6 with 2 because 2 is also eliminated. The precursor for 2 is 19. The precursor for 19 is 21. 21 the precursor is 18. 18 the precursor is 16. 16 the precursor is 14. 14 the precursor is 12. So 6 is to be replaced by 12 because 12 is continuing in the next level. No other possibility because we cannot continue writing the eliminated nodes in the second level of precursors. Similarly, look at 17. 17 is to be eliminated with, but can it be replaced by 16? 16 is also eliminated. Can it be replaced with 14? 14 is also eliminated. 12. So you are going to replace both 6 and 7 with 12 and 12. That means you require information from stream 12. Similarly, look at this. 10 is eliminated, having a precursor 8. 8 is eliminated, having a precursor 7. Right? So you can write 7 here because 7 is continuing. But what is the precursor for 7? It also is 12. Even if you write 7, doesn't matter. Similarly, look at 11. The precursor is 20. The precursor for 20 is 13. The precursor for 13 is 12. So you will be required to write 12. So we are left with only one stream which is 12. So you cut this stream. That should be able to, using this state stream, you should be able to solve the problem. Now you can see this is the only stream that I am trying to cut. So knowing this stream, I should be able to solve the separator to calculate 13 and 14. Then solve this reactor to calculate 20. Then solve this reactor to calculate 11. But can I solve this? I don't know 10. So I will not be able to solve this. But look at this side. So because 14 is known, I should be able to solve this unit to calculate 16 and 15. Then I should be able to solve the separator to calculate 17 and 18. Then I don't know 6, so I will not be able to solve this. But I will be able to solve this reactor to calculate 21. Then I should be able to solve this reactor to calculate 19. 1 is given, feed stream. So I will be able to solve this mixer to calculate 2. Then I will be able to solve the separator to calculate 3 and 4. Then I will be able to solve the separator to calculate 5 and 6. Now I know both the inputs to this mixer. So I should be able to solve this to calculate 7. Then I should be able to solve this to calculate 8. Then I will be able to calculate 10 and 9. Once I know 10 and 11, I will be able to solve this model to calculate 12. So starting with an initial approximation, we got an update and we were able to calculate the values of all the streams. If convergence is achieved, you stop, otherwise proceed with one more iteration. So you could see that this problem can be solved with only one tier stream. So that is the tier stream. Now let me take this example. Don't be under the impression that this is created. It is actually taken from a reference which belongs to a particular part of the flow sheet. Now how do we solve this problem? There may be a few other cases that come into picture, so please follow this carefully. Looking at this flow sheet, now you try to create the precursor list. Right? Now you can see several streams have got single precursors. Try to eliminate them while writing the second level of precursor. This is the precursor level 1. Right? Let me do that. So eliminate nodes with single precursors and create a new list. Cut the node which is having the largest number of precursors. In fact, in the previous problems, we never had this possibility. Now I am removing streams 1 to 5, stream 9, stream 12, 14, 15, 16 are all the streams which are having single precursors. But remember, when I am trying to write them 7 and 18, make sure that 7 is continuing, no problem. 18 is continuing, no problem. But here you have 20. 20 is being eliminated. So 20 is replaced by 19 because 19 is continuing here. Similarly, you can see 2, 3, 9. What is the precursor for 2? 1. Precursor for 1 is 5. Precursor for 5 is 6. So 2 is replaced by 6. What is the precursor for 3? 5. Precursor for 5 is 6. So writing 2 and 3 are replaced by 6. What about 9? It is 10. So 10 is continuing. So you have to make sure that the precursor list does not contain any one of the nodes that are eliminated. Now this is the second level. Now when you compare stream 28 and stream 30 have largest number of precursors which is equal to 5. If one of them is the largest, you will have to cut that, right? Otherwise, if there are two such arbitrary numbers, now you need to choose either of them, right? Either 28 or 30. So this is the tear stream that I am considering for the first cut. Now let us see to write the next level of precursors. Having decided to cut this tear stream, now what you need to do, wherever you have 28, that should be replaced. Our 28 is already guessed, so I need information from only 24. So wherever you have 28, that should be removed, and this is the next level of precursor. Now what we need to do, because these are the nodes which are having single precursors, they should be eliminated. So 25, 26 and 31 are being eliminated. Now if they are finding its place in any one of these precursors, please replace them with the nodes that are continuing. Now remember, the moment I have decided to cut this, I need not process this further. Now once again you can see there is only one node having largest number of precursors. I will be deciding to cut this, the second tear stream. So we are going to cut 30. So I will copy that information in the next slide. So this is the second tear that I am considering. Now this need not be considered further, but if you have 30 anywhere in this, you need to replace that. And because we are eliminating 25, 26 and 31, you should also be replacing that. Now after doing this precursors, updating the precursors list, now look at them. All of them have two precursors. So generally if that is the case, you need to choose arbitrarily. But be careful, you need to apply another rule. For the first time this case is coming up. Now look at the precursor for 24. The precursor for this particular stream 24 requires 24 itself as a precursor. So if this is the case, we call it as a self loop. You need to give preference to tear that first, irrespective of the number of precursors. For example, even here when you have 5 precursors, largest among all the precursors, but if you have a self loop, the self loop should be teared first, right? So this is considered to be self loop. So you can cut this stream 24. When you cut 24, what will happen? This becomes single precursor. It becomes 21. Here also it becomes 21, right? You need to update that information. So we have decided to cut this. So the next level of precursor is going to be, having cut this, this is the third precursor we are using. Now because we have cut 24, now these are going to become 21, 21 and so on. So now I need to eliminate these two nodes also because they are having single precursors. Now when you update this precursor list following the same principles, once again you can see that this is a self loop. Stream 21 requires 21 as a precursor. So you try to cut this. So again update your precursor list. So when you cut 21, now what will happen? Wherever you have 21, that is already addressed, so they are all going to become single precursors. But make sure that the precursor list does not contain any nodes that were eliminated till now, right? So we are left with this. Then we have only these two streams, all others are eliminated. Once again, if you look at either 6 or 8, both are forming self loops. 8 requires information from 8, 6 requires information from 6. It doesn't matter whichever is cut first. So I have decided to cut 8. When I cut 8, what I am left with, we are left with only 6. So you need to cut this. So finally we come across 6 tear streams to solve the problem. 6, 8, 21, 24, 28 and 30. Now these are the minimum number of tears required to solve the problem. So these are the tears that we have found out applying the algorithm. Now it is for you to identify the respective computational sequence. Now you can just check it up. This is what has been teared. This is also teared, 8, then 21, 28 and 30. So these are the streams that we have decided to tear. And where do you want to start? In which order you would like to solve these units is what is meant by computational sequence. You can verify whether you will be able to do these calculations or not. You have I. Where is unit I? Because I am tearing 6. This is the only input to unit I. So I will be able to solve I to calculate 5. Once I know 5, because this is the only input for D, I will be able to solve D to calculate 4 and 1 as well as 3. Then A, this is the only input to unit A, so I will be able to calculate 2. But will I be able to calculate E? I don't know 9, so I may not be able to calculate E. But look at this, after A, I am coming to H, this is the only input to H, so I will be able to solve H to calculate 14. Then solve N to calculate 15, then solve O to calculate 16, then will I be able to solve P? No, I don't know 17, so I will not be able to solve P. So after O, now where I am going? Yes. Now will I be able to solve this? This is the only input to unit S, so I will be able to solve unit S to calculate 29 and 27, then you can solve M because already 30 is teared, so both the inputs are known. I should be able to calculate 31, then R. Now you can see, do we know after M? Yeah. I think there is a small mistake I might have missed. Probably you need to, because 21 is teared, I need to solve L to calculate 22, stream 22. Now this is the only input. I need to solve Q. Q cannot be solved because 25 is not known, right? So you can check it up. So just check up whether this computational sequence is going to be alright, or identify based on the tear streams that you have decided whether you will be able to solve all the units and calculate all the streams involved in the problem. Yeah, there is some other issue, but I may not be addressing that here. So the first, when you present a problem to a simulator, when you draw a flow sheet, the simulator will have to apply the algorithm to check whether there are any possibilities to partition the problem into subparts or not. And if it is possible, what are the number of parts and in what order these parts need to be calculated. We have seen this algorithm as well. Then for each of these partitions, if you need to identify the minimum number of tears that are required. Then identify the computational sequence. So these are the background calculations the simulator will be making, even without, you may not be even aware of some of the complexities that are involved in the background. So with this, I would like to close this session.